So, hello everyone. So, welcome back to the Möbius Seminars. So for those who are joining for the first time, so just a recap about the scope of this seminar. So, the idea is to bring together two communities that have common interests from different perspectives. So, philosopher and physicists. And for us, physicists in particular, it's an excellent occasion, like to step back a bit from our everyday business and research activities, to think more and to question our methodology, the way we do science, and also fundamental concepts that we use all the time, but we not question too much. And in that context, learning a lot from a philosopher of science and physics. So today we are glad to have Professor Thomas Ryckman, who is a professor of philosophy at Stanford University, specialist of the question of philosophy of space-time and relativity. In the topic, he published, among other, lately a book about Einstein and the central role epistemology had on his work and on his discoveries. Today's conference will be more specifically about the question of the nature of space-time and the debate, the long-standing debate about substantivalism and relationism approach about space-time. So, Thomas, the floor is yours, whenever you want.
Well, thank you very much for the invitation to give this seminar. I've taken Henri's advice and suggestion that I try to just fill in for physics people something of the history of the philosophical debate between space-time or space substantivalism and space relationism or space-time relationism. And I think that my purpose is primarily simply to fill in the pieces of background so that you might be able to recognize how some of these debates are playing out in fields that you might be working in. I don't pretend here to give you anything new. What I'm giving you today, this seminar, is largely just a very concise précis of a course I've taught at Stanford for 20 some years. I'll go from there. It's a historical course. It really picks up with Aristotle, and it goes all the way to quantum gravity with Carlo Rovelli and Lee Smolin and Ed Witten and string theory and things. So moving on, I thought that what we could do first is, let's see if I can. So you saw on the Möbius strip these gentlemen, and they are all gentlemen, I suppose, starting with Aristotle. And there's a line of argument or influence that you can trace through the generations. And I've tried to indicate that with these lines of influence. I can't talk about all of these people today. Obviously, I've had to make a selection just simply to put up the most salient issues of how space-time substantivalism and relationism come to bear in contemporary research. Okay, so I won't linger long on this, but obviously much of modern science begins in the 17th century with the problem of motion and overcoming the scholastic Aristotelian prejudice, if you like, for rotary or circular motion as being perfect motion, eternal motion, because it's the motion supposedly of the celestial spheres. It's a motion without beginning or end, whereas rectilinear motion, translational motion, is finite and perishable and incomplete. And of course, the scholastics recognized that the combination of rectilinear and rotary motions was possible, and that was a violent or unnatural motion, which bodies exhibited when they were moving or forced to move, I should say, away from seeking their natural place in the Aristotelian cosmos. And you can see the preference for Aristotelian circular motion simply in these three cosmos, if you like, from Ptolemy to Tycho Brahe to Copernicus. Of course, it was Kepler who first told us that the orbits are not exactly circular, but the prejudice for Aristotelian circular perfect motion certainly lasted through the Copernican revolution. It lasted even into this famous book by Galileo, which is a book-length argument for Copernicanism. But also, we think of Galileo as the founder of the modern concept of inertial motion, but in fact, that comes from his two new sciences a little later in the 1630s. In this book from 1632, the Dialogues on two chief world systems, he is still in the mode of thinking about inertial motion as circular, because again, that's the Aristotelian tradition, even though he's arguing against the scholastics and saying that the Earth is moving. Galilean relativity is in this book, and a famous passage being shut up in the cabin of a ship, and whether the ship is moving very smoothly on a body of water, or whether the ship is at rest in harbor without rocking. Any experiment that you could perform inside a cabin without windows, you couldn't tell whether the ship was in uniform motion or at rest. And here's the example from dropping a cannonball from the crow's nest, as seen both from the frame of the moving ship and from the resting observer on the shore. Well, these new concepts in the 17th century, what is the natural state of a body? It's no longer its telos, it's seeking its end state, but rather is it at rest or is it in uniform motion? But of course, the question is not directly posed by Galileo. At rest or in uniform motion with respect to what? With respect to other bodies or with respect to some containing background space? The early text of Newton, De Gravitatione, defines the inertia as the endeavor of a body to retain its state or to resist its change of state. Newton, of course, is interested in the origin of inertial mass, quantity of matter, as he says it, but he doesn't really tell us anything about it. And the problem of the origin of inertia is not really an issue that's addressed directly until Ernst Mach in the second half of the 19th century. Of course, that's going to be a story that's about mass, which is a core concept in classical mechanics. And we have to recognize that it was Galileo who showed, I think, demonstrably that free fall, gravitational motions are accelerations. So the question of motion, is it relational? Is it absolute? Is it a relation between bodies that's in principle an observable relation? And the canonical example here is sitting on a rail car and at the station, not feeling any jolts and noticing the train next to you in motion with respect to where you're sitting. And you're not sure at first whether your train is moving or whether it's the train on the other track. The canonical example of an absolute motion, which is a motion between a body and a containing background, whether it's space or space-time, would be something considered by Bishop Berkeley, for example. He says that we're not really able to conceive this. Some people think that we can. Some people doubt this. Can you imagine a perfectly rigid spherical body in motion with respect to a completely featureless, empty background space? So you can't track the motion of the body with respect to fixed stars or anything like that. It's just a completely black background space. Can you think of the body as somehow being able to distinguish whether the body is moving or whether it's at rest? Now, there are two related dichotomies that are going to show up, and they even play a role in contemporary views about space-time substantivalism and space-time relationism. And that's a distinction between views that are more empiricist and views that are more rationalist. And generally, you're going to think that the rationalists are going to be those people who are committed to absolute motion. What does a rationalist view hold? Well, that there are necessary truths of metaphysics, and they're not things that we learn from experience. They're a priori truths that we can see the truth of by inspection or by having been implanted in our minds by a divine being. A rational truth for Leibniz, of course, is the principle of sufficient reason. It's the hinge on which all of Leibniz's philosophy pivots. So rationalists are going to support absolute accounts of motion in general, where existence is not tied to observation, but rather to metaphysics. Empiricists, on the contrary, are going to be attracted more to relational accounts of motion, because empiricist demands that what exists can in principle be observed, and that any necessary truths that there are either definitional or purely analytic, like the truths of arithmetic. Now, empiricists insist on a relational account of motion because it's an observable relation between objects that can be seen. A motion between the body of interest and bodies that are considered at rest that are observable. So empiricism and relational accounts of motion tend to go together. On the other hand, you have this funny situation where Newton, who is widely celebrated by empiricists like Hume, and in many sense Hume, and Leibniz, who is in many ways the canonical rationalist in philosophy, are kind of quasi-empiricists about motion. And it's a quasi-empiricism that says that, well, look, only motions are observable. We need to have absolute motions with respect to absolute space in order to do dynamics, in order essentially to define accelerations. And Leibniz's quasi-empiricism is a little different, but it's a quasi-empiricism because, of course, it's going to be based on the principle of sufficient reason. But for Leibniz, it must be possible to observe motion. And if you can't observe motion, it's just a figment of your imagination that a body is moving. Space and time, on this view of Leibniz, and we'll see this in a minute, are simply, without bodies, space and time are simply relations. They're ideal relations of coexistence and succession. Abstracting away from all bodies, they're merely ideal relations of the mind. And these arguments of Leibniz were widely known. Much of Leibniz's corpus was not widely known until really into the 20th century. But, well, I should say the edition of Gerhardt in German in the mid-19th century. But most of Leibniz's interesting metaphysical works were not widely known and studied until the 20th century. But one text was, and it was the correspondence with Samuel Clerk, who was essentially Newton's parish pastor in London when Newton was living in London and was master of the mint and was busy hanging people who were clipping coins, having retired from Cambridge and had been given a sinecure in London. And it was a correspondence that originated in 1716, ended in 1717 with Leibniz's death, and was published shortly thereafter by Samuel Clerk. It was a correspondence published in English. Leibniz wrote in English to Clerk. There's a long and interesting background about the Leibniz-Clerk correspondence about how George of Hanover, who was invited to be George I of England, was invited to be King of England, the English having exhausted their royal lineage at that time, and looking around for a good solid Protestant, they found one in Hanover. And Leibniz was his principal courtier, but he could not bring Leibniz to London with him because of the controversy with Newton over the calculus. And Newton had made Leibniz absolutely toxic in Great Britain as a plagiarist. And we know, of course, that's not true. We know that it was independently discovered and promulgated, but Leibniz was certainly persona non grata in Great Britain when George I became King of England. Well, according to Leibniz, absolute space violates the great principle of sufficient reason, the metaphysical principle on which all of Leibniz's metaphysics hinges. And he says this in various places in the correspondence. He says, if space is absolute, if it's perfectly uniform so that one part of space does not differ in any respect from another part of space, then something would happen for which it is impossible that there would be a sufficient reason. And an example of this, suppose God, preserving the same situations of bodies among themselves, places them in space in one place as opposed to another, for example, by transforming east into west. That's Leibniz's example in his third letter to Clerk. That would be a change without a discernible change. So it's not in accord with the principle of sufficient reason. If it's a change without a discernible change, there's no reason for it to happen, therefore it doesn't happen. And you can see here that the principle of the second Leibnizian principle, which is a corollary of the principle of sufficient reason, is the principle of identity of indiscernibles, where Leibniz says, I infer from the principle of sufficient reason, among other consequences, that there are not in nature two real absolute beings indiscernible from one another, because if there were, God and nature would act without reason in treating one otherwise than the other, and that therefore does not produce two pieces of matter perfectly equal and alike. That's one of Leibniz's arguments against atomism, actually. And he says again, if there are no good reasons for a choice, then good reasons for a choice are not to be found where everything is indiscernible. So this notion of discernibility is related, of course, to the notion of observability. If you cannot observe a distinction between two things, then you're not looking at two things, you're looking at one thing, counted twice. Here's the East-West thought experiment of Leibniz. It's just a reflection about a mere axis. And no distinction between right and left-handedness, which we know is not strictly true today, but that was a surprise in 1956. There's another Leibniz thought experiment of just translating the whole world, by which he means all the observable universe, from one region of space to another region of space. And of course, this would be a violation of the principle of sufficient reason and the principle of identity of indiscernibles. The situations would be indiscernible, therefore, they're not two things, but one. Just by way of a footnote, I give an entire couple of lectures on Euler, who is a very interesting case because he, more than anybody else, modernized Newton's mathematics and physics or mechanics. But he was a rationalist, a Leibnizian in metaphysics, and he has some interesting arguments about how we need to support absolute space as a consequence of the principle of sufficient reason. I should mention that Christian Wolff, who was the great Leibnizian at the time in Germany, said that Euler was a baby in everything but in mathematics. Leaping ahead, I want to jump right to Ernst Mach and the influence that Mach had on Einstein. And I think you could make a pretty strong case that the philosophical influence of Mach spurred Einstein to seek a relativistic theory of gravity. And it's above all the criticisms that Mach lodges in his book on mechanics from 1883, where he cites and criticizes those famous passages in Newton from the Principia, the Scholium to the definitions, where Newton is outlining the arguments for absolute space and time. And this, of course, is the Newton argument about the rotating bucket. I'm not going to go into it here. You've probably all read this or heard of it. But Mach proposes in his mechanics, well, what would happen if the walls of the bucket were several leagues thick and were rotating, and a sufficiently massive bucket, according to Mach, might in fact drag the inertial frame of the water with it, leaving the water surface flat. We'll see that something like that is very, is in fact true. I've got to bypass a lot of work here. I'm not going to talk about the whole argument. That's a big part of what I do in the course, working with the famous whole argument and how Einstein thought that he couldn't have a generally covariant theory of gravity on pain of violating determinism. I'm not going to go into that now, but he was confused about the meaning of general covariance, which, as we know today, is just a formal requirement on theories on how you write them down in tensor form. It has nothing to do with the principle of relativity. Einstein thought it did. He even realized that was a mistake, and he still refers indifferently through the rest of his life to the principle of general relativity when he means the principle of general covariance. You have to love somebody like this. And of course, the lesson of the whole argument, or the Lochbetrachtung, is that space-time coordinates have no physical significance. You could say that that means that the topological points of a bare manifold have no ontological significance at all. They're merely mathematical props. And a point of a manifold is not a physical point of space-time until a metric field is defined dynamically on that space-time. And here's Einstein's final word at the end of his life on what he learned from the whole argument and retained ever since when he climbed out of the hole, as it were, in the autumn of 1915 to formulate general relativity. On the basis of the general theory of relativity, space as opposed to what fills space has no separate existence. If we imagine the gravitational field, that is the functions g mu nu, to be removed, there does not remain a space of the type of Minkowski, but absolutely nothing, also not topological space. He says then there is no such thing as an empty space, a space without the field. Space-time does not claim an existence on its own, but only as a structural quality of the field. That is an anti-substantivalist statement. Einstein did try to carry out the Machian program of relativizing inertia. This is apparent in several places, notably in section 2 of the canonical presentation of the new theory in April 1916. He considers these fluid bodies rotating at some distance in space. Newton had a very similar idea of two bodies connected by a cord. Here the cord is removed. You're just looking at the round spherical fluid bodies. And according to the observer at rest on one, the others rotating with a constant angular velocity. And similarly, the second observer thinks that of the first body. But by intrinsic measurements on the bodies, Einstein tells us, the first sphere, S1, is found to be an ellipsoid of rotation. But he says, well, rotation with respect to what? He says the supposed absolute frame of S1, and this is involved in Newton's explanation of centrifugal forces in the bucket experiment. It's the rotation of the bucket with respect to absolute space that explains the centrifugal forces that are observed in the rotating bucket. He says the rotation of the sphere with respect to an absolute space is merely a factitious cause of the change in shape between the two bodies and not a thing that can be observed. And he says the true cause of the difference in shape between the two spheres must lie outside the system under consideration, he says, in masses which we have not included in the system under consideration. And he said that the special theory of relativity inherited this epistemological defect of Newtonian mechanics, a defect that was first clearly pointed out by Ernst Mach. And in 1916, when Mach died, Einstein wrote a glowing obituary, essentially telling the world that if Mach had not been crippled by a stroke in the late 1890s, Mach himself probably would have discovered the relativistic theory of gravity. Thinking about Mach's principle in relation to the general theory of relativity, Carlo Rovelli lists 8 different formulations in his book on quantum gravity. I think they're very interesting because he goes through them one by one and actually tells us what the evidence is for these different formulations. Can distant stars affect the local inertial frame? Yes. Is the local inertial frame completely determined by matter in the rest of the universe? No, it's not completely determined. The gravitational field has independent degrees of freedom. The rotation of an inertial reference frame inside the Newton bucket is dragged along by the mass of the bucket. And this effect increases with the mass. This is true. This is the Valenza-Therian effect. And actually, this has been demonstrated. The famous gravity probe B experiment run by my friend Francis Everett in the physics department, a 50-year-long experiment where they had to develop the technologies for these cryogenic gyroscopes. They didn't have that in the 60s when this was all planned. But it did actually show that there are these effects that were predicted by Mach. Okay, in the limit in which the mass of the bucket is large, the internal inertial frame rotates with the bucket. That depends on how you take the limit. No global rotations of the universe, that's false. We have a Gödel solution that tells us that there's a solution. In the absence of matter, there would be no inertia. That's false. That was false already in the de Sitter world from 1917. There's no absolute motion, only motion relative to something else. That's the basic physical idea of the general theory of relativity, according to Rovelli. And the local inertial frame is completely determined by the dynamical field of the rest of the universe. That's precisely Einstein's key idea, according to Rovelli. So these Machian influences run deep. They run even to relativistic cosmology. And this is the paper that created relativistic cosmology in 1917. And if you don't know the story, it's a very interesting story. It's Mach basically being the spur to Einstein to create global solutions where we don't have boundary conditions at infinity, which are going to be absolute, in some sense, the boundary conditions of Minkowski spacetime. So what does Einstein do? He closes up the universe. He makes the universe finite. And that means he has to add the cosmological constant to do that. It's a long and complicated story. It's a wonderful story, but philosophically, it's summarized in this one passage from this paper. Einstein says, in a consistent theory of relativity, there can be no inertia relative to space, but only an inertia of masses relative to one another. If I remove a mass sufficiently far from all the other masses of the world, its inertia must drop to 0. Of course, Einstein's universe in 1917 is not the one that we lived in. It was static. We know that static universes are unstable. And that was shown by Friedman and Lemaitre in the 1920s. But the global solutions of the field equations for Einstein had to implement this relativization of inertia that Einstein took from Mach. And here's Einstein's formulation of Mach's principle. This is the last formulation where he explicitly endorses Mach's principle, where he says the G field, the inertial gravitational field, is completely determined by the masses of bodies. One of 3 principles in 1918 on which he said his theory rests. Okay, so what happens to this issue of absolute versus relative post Einstein, post general theory of relativity. Well, I think Einstein was a little unclear about this and certainly not transparently obvious about it. But Hermann Weyl, as one might expect, nailed it perfectly. He says in his book on philosophy of mathematics and natural science from 1926, he says the experiences which prove the dynamical inequivalence of different states of motion teach us that the world bears a structure. And what is that world structure? It's the affine structure of the world of space-time, which is, we know, uniquely determined by the G mu nu. And Weyl goes on to say, without a world structure, the concept of relative motion of several bodies has no more foundation than the concept of absolute motion of a single body. And this is the way that we think about it today. Weyl gives us a very interesting example of an active diffeomorphism, able to distinguish between active and passive, as Einstein wasn't at the time. He says, without affine structure by general covariance, all the particle world lines could be continuously deformed to become vertical straight lines. This is with active diffeomorphisms that would eliminate all distinctions of relative motion. So these, in general theory of relativity, you do have a moderate notion of absolute motion. That is, that rotations and accelerations are determined with respect to affine structure. And this is absolutism in the sense that whether a body is rotating or not, without reference to another body, is perfectly well determined. It's determined with reference to the structure of space-time. It's relationism in the sense that rotational motions are not defined with reference to a space-time fixed background, but with reference to an affine structure, which is not fixed, but which is going to be dynamically determined by the metric. I didn't say much about the whole argument. I hope everyone has some, at least remote acquaintance with that. But how it appears in contemporary philosophy of physics can be looked at, and I'm going to think of it now in terms of manifold substantivalism versus manifold relationism, as we see this through the modern notion of active diffeomorphism. And we can talk in this way with active diffeomorphisms of Leibniz equivalent general relativistic models, which are going to oppose manifold substantivalism. Substantivalism about the space-time manifold. So what is manifold substantivalism? This is the view that the physical world contains not only aggregates of matter, physical objects and their spatiotemporal parts, but ontologically independent of these, space-time and its different parts, region, points, whatever. And many philosophers of physics, at least in the last 20, 30 years, thought that the ontology of a physical system is at least partly comprised of properties of space. And this would include relations between adjacent points of space. Space-time relationism, on the other hand, is the view that the physical world contains spatiotemporal aggregates of matter. These aggregates are related by various geometric and non-geometric relations, but the physical world does not contain, in addition, a space-time over and above these aggregates of matter and their interrelations. And here's the text that really laid this out for the first time for English reading physicists, relativists. It's the text of Hawking and Ellis, a very good text. It's the first text in English, and I have to put English here because I'm sure that Lischnerowitz or Schuchet-Broha or somebody like that has written a French text where all this was obvious in the 50s. But it didn't percolate over into the English literature until this text of Hawking and Ellis in 1973. It treats general covariance as the requirement that diffeomorphically related space-time models are physically equivalent. And that we call Leibniz equivalence. Here's what Hawking and Ellis say. He says, they say, the mathematical model we shall use for space-time, the collection of all events is a pair, mg, where M is a connected Hausdorff C infinity manifold and G is a metric. Two models MG, M prime, G prime will be taken to be equivalent if they're isomorphic, that is, if there is a diffeomorphism theta, mapping M into M prime, which carries the metric G into the metric G prime, that is theta star, G equals G. Speaking then strictly, the model for space-time is not just one pair, MG, but a whole equivalence classes of pairs under the diffeomorphism, M prime, G prime, which are equivalent to MG. This was, I think, absolutely revelatory for clearing up the meaning of general covariance in the English-speaking physics literature. And in Einstein's theory of gravity, this general covariance or invariance of laws under active diffeomorphisms, the group diff-M, expressly forbids individuation of points of the space-time manifold as spatio-temporal events. It gives rise to this notion of Leibniz equivalence. That's the equivalence class under the diffeomorphic mappings. And the equivalence class simply says that you cannot say that one of the equivalence class is the real situation and the others are somehow false. There's all the same situation viewed just differently. And here's the Leibniz shift argument against manifold substantivalism. If we suppose that the field equations of the general theory of relativity are diffeomorphically invariant, that M prime is the model just in case M is, then the manifold substantivalist must maintain that these are physically different, though indiscernible situations. You can see why this is called Leibniz equivalence. And you can formulate it this way, slightly more in terms of these model theoretic terms, that the Leibniz shift leaves the physical structures unchanged. And you want to say that an indiscernible change is not a change at all. You can bring the principle of sufficient reason and the principle of identity of indiscernibles to bear against manifold substantivalism. And you just want to say the bottom line here, that the space-time manifold is just this equivalence class of diffeomorphically related models. According to this well-known paper of John Ehrman and John Norton, and again, I think this paper was premised on the appearance of Hawking and Ellis's text. The acid test of manifold substantivalism is drawn from Leibniz. If everything in the world were reflected east to west, or better translated 3 feet east, retaining all the relations between bodies, would we have a different world? The substantivalist must answer yes, since all the bodies are now in different spatial locations, even though the relations among the bodies are unchanged. The diffeomorphism is the counterpart of Leibniz's replacement of all bodies in space in such a way that their relative relations are preserved. In some, substantivalists, whatever their precise flavor, will deny Leibniz equivalence. Diffeomorphic models represent the same physical situation. Well, substantivalists are clever people, so they come up with a version of substantivalism that is going to respect Leibniz equivalence. And this is called, by some, metric field substantivalism. And in this view, substantivalism requires only that space-time is a kind of thing that can, in consistency with the laws of nature, exist independently of material things, and is properly described as having its own properties, over and above the properties of any material things that may occupy parts of it. For example, measurable space has energy. Empty space has measurable energy. This the value for the accelerating expansion of the universe, discovered in 1998, would be that. And so therefore, the substantivalist has to count the manifold M together with the metric G as representing space-time, not just the manifold M, but the manifold plus metric. And this is now a model of a general relativistic space-time. And of course, this is going to respect the diffeomorphic equivalence between space-time models. This is a sophisticated substantivalism. It endorses this anti-hexatism, this idea. Hexatism would be the idea that there's a difference, even though there's not a discernible difference. Well, anti-hexatism insists that there is a discernible difference between possible worlds. And both space-time relationism and metric field substantivalism are going to agree that in the general theory of relativity, the metric field represents something genuinely physical and is a fundamental entity. I wanted to quote Rovelli because he actually has, there's no knockdown argument. We don't have really knockdown arguments so much in philosophy, but we see that we do make progress because what we talk about changes its colors as we go through the centuries. It acquires new contexts and new associations, and the dialectic changes as a result of that. But here's Rovelli on why he's not a metric field substantivalist in his approach to quantum gravity. He tells us a substantivalist position can still be defended to some extent. Einstein's discovery is that Newtonian space-time and gravitational fields are the same entity. This can be expressed in two different ways. One states that there is no space-time, only the gravitational field. This is the choice I have made in this book. The second states that there is no gravitational field. There is space-time that has dynamical properties. This choice is common in the literature. I prefer the first because I find that differences between the gravitational field and other fields are more accidental than essential. But the choice between the 2 points of view is only a matter of choice of words, and thus ultimately personal taste. However, the second choice is a very weakened substantivalist position. One is free to call space-time anything with respect to which we define position. But to what extent is space-time different from any arbitrary continuum of objects used to define position? The characterizing feature of space is that of being truly distinct from moving bodies, of being truly distinct from dynamical entities such as particles or field. This clearly is not the case for the space-time of general relativity. So I'm almost through. I'm just going to wind up here with another comrade in the loop quantum gravity program, Lee Smolin, who actually defines relationism quite explicitly in 3 terms: R1, R2, R3. R1, there is no background, no space-time background. R2, the fundamental properties of the elementary entities consist entirely in relationships between these entities. And R3, the relationships are not fixed, but evolve according to law. And the time is nothing but changes in the relationships and consists of nothing but their ordering. So you see, these are not only relationist views, these are Leibnizian views. And the relational strategy, which Smolin thinks is the productive strategy to follow in quantum gravity, is to seek to make progress by identifying the background structures in our theories and one by one removing them, replacing them with relations that are subject to dynamical laws. So removing fixed background structures, replacing them with changing dynamical laws. And so the bottom line is that the debate between absolute and relational in the context now of quantum gravity becomes background dependent versus background independent. And this is picked up by Rovelli. The key conceptual difficulty of quantum gravity is to accept that we can do physics in the absence of the familiar state of space-time. This absence of the familiar space-time stage is called background independence of the classical theory. Technically, it is denoted by the gauge invariance of the action under active diffeomorphisms, which is a consequence of 2 properties of the action. It's invariant under arbitrary changes of coordinates and the fact that there is no non-dynamical background field. Well, how does this contrast with other approaches to quantum gravity, notably string theory? Well, string theory is in line with conventional quantum mechanics and quantum field theory as a background dependent theory. There are background structures, there's a background geometry, structures that are defined independently of background, like inner product, external clocks, and observers. And so you have two options. You have the background dependent option, which is to give up relationism, quantize gravitational waves on fixed backgrounds using conventional methods of quantum field theory. This could be perturbative quantum GR or string theory. And you have background independent ways, like perturbative quantum GR could also be semi-classical gravity. Background independent ways find a way to define quantum theory, which is relational and applies to relational theories. And this would be things like causal sets of Raphael Sorkin or loop quantum gravity. And the aim of a loop quantum gravity approach to the subject is a robust method for quantization of diffeomorphism invariant theories. So here's my last, the takeaway. The issues of space-time relationism and substantivalism are as old as modern physical science. They have not disappeared, but the dialectic has changed, and the debate continues to influence research programs in quantum gravity. So thanks very much for your attention.